All right, it's 11 o'clock and welcome to another Chai and Wine. Today we have a very special Chai and Wine in the sense that we are going to present some advanced optics in magneto-optics. And today we have Dibyasankar with us to speak about it. So Dibya is an integrated PhD student at TIFR. He joined TIFR in 2017 after finishing his bachelor's from Ruparel College at Kolkata. He is a very avid outreacher as well and a cyclist. So, Dibya, all yours.
Yeah,
Share.
yeah, I will share. This thing you were in a practice session. Is it this?
Yeah.
Okay, shall we start then? Okay. So, good afternoon. I am Dibyasankar Das. So, as Ullas told, I am originally from Kolkata, but for last 6.5 years, I am in TIFR doing my PhD here in Department of Condensed Matter Physics and Material Science. So, today what we will discuss is basically my title. So probing ultra-thin semiconductors using magneto-optics. So that is basically my PhD work. But what is the goal of my talk? What I want to do is that at the end of the talk, you should understand all the words in this title and also this image, what is meant by this. So if that, at the end of the talk, you say that, okay, I can understand the title and I understand this image, then it's fine. The goal is satisfied. So just to start, I don't know how many are there in online, but whoever is present here, so I will just have a count, like how many of you know what is a semiconductor? So at least you know where it is applied, and even if you don't know how it works, but you have heard the name semiconductor. Then do you know about anything, say optics? What? Okay. So do you know anything about optics? What is meant by optics as such? Any of you? No. Okay. So we learned that what is meant by optics. And then ultra thin. What is meant by ultra thin? Any guess? Like a thin material, if you think of the paper is a thin material, our hair is thin material. But what is the dimension of our hair? The diameter, those things. Or what is the thickness of a paper? Microns. Okay. So you have some sense of micron. What is a micron? So in that level, we'll see what is meant by ultra thin. Okay. And then there is a significant portion will be, so there is magnet involved there. So some part will be about magnet. Of course, you all know about what is magnet. But let's start with semiconductors. Okay. What is the theme of the today's talk actually? So what is a semiconductor, if I want to describe? So we all know that this is a conductor. Okay. So what he does, he conducts orchestra. So the semiconductor will be looking like this. It's a semiconductor. But this is some, Western version. If I want to place it in Mumbai context, so this is a base conductor, and this is base semiconductor, maybe. But if you think that I'm cracking that joke, then it is a very poor joke. But I can ensure that there is a very famous book in our field that is The Fundamentals of Semiconductor Physics and Material Properties, written by two giants of this field, Yu and Cardona. So in their, after the preface, they have a figure like this, where this conductor is actually cheating what is written there. So it's shown that what you should do. So in that sense, he is actually a semiconductor. It was written like that. So I'm not the only one who is cracking this kind of poor jokes. But anyway, to more scientific definition. So they're everywhere. We know that. Okay. So you just name it, your cell phone, your computer, this TV, the we are talking now. This is live stream to YouTube. Everything is semiconductor. You just name it, anything that will be. I mean, they should have some semiconductor part in it. Okay. And so you're using it knowingly or unknowingly, but you're definitely using that. But if I want to give some definition, what is a semiconductor? So this is semiconductor basically is a switch, simple switch. So what Rahmanji is doing now is turning on something. So anything, say fan was off, if I switch it on, it will start to conduct. Okay, so the electricity was kind of stopped by that switch, and I switch it on, the electricity flows, and some device works. So semiconductor is exactly like that. So it works as a switch. So we are familiar with this kind of switch. What a switch does is that it stops the conduction of current. So most of the time, it will actually block the flow of current. Okay, so it will act as an insulator. But in insulator, whatever you try, you never can flow any current through that. But in semiconductor, if you force the material, then it will start to conduct. Okay, so that's why it's called semiconductor, because most of the time it cannot conduct, but you can make that material conducting at your will. Whenever you want, you can make it conducting. But then semiconductor is also a switch, and that switch is also a switch. Then what is the difference between a semiconductor and a switch? Three things. One is that it's extremely small. So that switch is in centimeters, centimeters cross centimeters. You can think of, say, millimeter cross millimeter switch. But the semiconductor switches, what we are talking about, those are in nanometers. Okay, 1,000 times less than the thickness, 100,000 less than the thickness of our hair. That is the dimension of that switch. So it is extremely small. The other thing is it's extremely fast. How fast can you switch on and off a switch? A normal switch. Say one in a second, two in a second, very fast, 4 in a second. But they work in a gigahertz. So in 1 second, they can switch on and off in 10 to the power 9 times. So it's extremely fast. And the other thing is, which is very, very important, which is it is a static switch. So in that switch, this kind of switch, you need to move a part. A part should go down and up like this. So some part is moving. That's why it's kind of limiting the frequency. So in a second, how many times you can switch on and off? That is because there is a limit how fast you can move that object. So, but these semiconductor switches are static. They remain in a place and then switch on and off like that. There is no moving part. So these are very useful thing about semiconductor. Okay. So now if I go to a more scientific definition, so don't get carried away about the names and the figures. I will explain everything. Just go by my words. I think you will understand everything. So this blue band is called conduction band. It's a block of something. So it is an energy scale. So there is a band of energy, and this pink one is another band of energy. What is the difference? The difference is when an electron, we all know about electron, right? Okay. So when one electron is in this pink band, it cannot conduct electricity. Okay. As soon as it goes to this blue band, it starts to conduct. That is the difference between blue and the pink. So if you see in case of a metal, so this is called valence band, and this blue part is called conduction band. So if you see in case of metal, this kind of overlapped. So whatever electron is in the pink band, they're also in the blue band. So there are always electrons available to conduct. So that's why they're conductors. Okay. But if you see the other extreme, this is a insulator. There is a huge, this is called band gap. There is a gap in the energy. So even if an electron try to go there, it needs this much amount of energy to go to hop from here to here, which the electron doesn't have. So all the electrons will be in this part, no electrons available in this part, so the material will not conduct. But if you see in case of semiconductors, they are close. So this is not like metal, they're not overlapped. It's not like electrons are available all the time everywhere. But you can give this much amount of energy and excite one electron from this level to that level and make the material conductive. Okay. So the kind of order of energy gap is in some unit, which we call electron volt, but don't bother about that, some number 3.2. But for this case, it will be 6, 7. But then what is the, what you have around you, which has an energy of say 3.2 electron volt. Then say if for 3.2 electron volt, you need a generator of 15 kilos to just provide 3.2 EV, then it's not useful. We are all using this semiconductor device in our phone, and this energy should be very small. That's what I wanted to mention. Now, the principle is this: you give some energy, so the electron will excite from here to this valence band to conduction band, and it may conduct. But similarly, once the electron is there, you see some electron deficiency in this pink band also. So electron was there, but now that electron got excited, so it has left a space where it was. So we call this thing as hole. Hole is understandable. There was electron, the electron is removed. Now there is hole. So we call this thing hole. So once electron is created, then it creates a hole in the valence band. So electron is positively charged, so the hole will be electron is a negatively charged, the hole will be positively charged particle. Okay. So hole is nothing but deficiency of electron. So now once there is an electron in the valence band and conduction band and a hole in a valence band, then that electron can come down to the valence band and give the same energy it received while going up. Okay. So this is the energy conserved process. If you give energy, it will jump to the conduction band. When it comes down to the same level, it will release that energy. Okay. So now the question is from where we can get this 3.2 electron volt kind of energy. So, oh, sorry, before that, oh, I forgot. So now these are some abstract things, like if this axis has energy, this axis has nothing, so electrons are created from here to here, what does it mean? But if you think about this in a realistic scenario, say this is a block of crystal. So say a silicon, the name we are familiar with, say a block of silicon. And then you somehow excite one electron from somewhere to somewhere, and it leaves a hole where it was. But now electron is a negatively charged particle, and the hole is a positively charged particle. So a positive charge will attract a negative charge because there is Coulomb interaction. Okay, Coulomb interaction means this thing, like a positive charge attracts a negative charge. So now as soon as this electron is created, the hole will say, "Nahi, tum to idhar se." We have some negative hai, positive, there is some attraction. So then they will bind to each other. But this is not actually a particle. It was not there. I have created. So that's why we call it quasi-particle. It's not particle. And as physicists, we love to give names like conduction band, valence band, this and that. So we have gave this exotic thing the name exciton. It's understandable, like exciting something. So the electron, exciting electron, exciton. It's kind of that. So this quasi-particle, the Coulomb-bound electron and hole in the material, we call that exciton. In the future of my talk, this concept will be very useful. So if you have any questions, just clear this thing up now. And other thing, like I'm speaking in English, though English is also not my mother tongue and none of our mother tongue also. So you can ask question in Hindi, Marathi. I don't understand Marathi, but Ullas is there. Ullas will translate. Yeah, translate the Marathi to me, and you can ask the question in any language. And if there are any question in YouTube also, we'll clear this up here and then go forward. Okay. अगर कोई question है इधर से, if you have any question, yeah. No. Good question. So once I put the energy there, if you see there in the band structure, they're separated. So if it wants to recombine with that, it can recombine, but then you have to release that energy. By keeping that energy, it cannot recombine. So this thing is basically this energy, this plus this. This structure is an exciton. You need a energy source. So as soon as it can recombine, I mean, there is attraction, the electron can go to the hole and they will annihilate. But then you have to release this energy. You cannot keep the energy as well as there will be nothing. That cannot happen. So this structure, energy plus hole and electron, this structure is an exciton. And it's a dynamic process. So if I keep shining light, some electron will get generated, will form exciton. It will form exciton and then they will recombine. But on average, there will always be available, and some excitons will be available in the system. Okay. Okay, I'm going ahead then. So now, if you see, so we are in the semiconductors. Now we are going to optics part. Okay. So two things, probing and optics. So how we are probing these semiconductors using optics. So optics means basically light. Okay. Any kind of light. So optician, we call this, who makes this specs, we call it optician, or the doctors, we call it opticians, is because they deal with light. So optics means light. And we all know, though I'm not sure about you, but we have, a range of light. A very small part of it, we can see the VIBGYOR part, but X-ray is also a light, radio is also a light, mobile communication, microwave, infrared, remote, gamma rays, all these things are basically light. The only difference is, you see, the distance between these two peaks keep decreasing. That is the only difference. Otherwise, it's all light. So it is our deficiency is that we can only see this part of the energy. Our eye is sensitive to that part of the energy, and that's why we call that visible spectrum. Okay. But now if you see the energy corresponding to the visible spectrum, the red is 1.77 and the blue is 4.14. If you can go to little infrared, beyond red, it will decrease. So 0.6, 0.7. You remember this is the same energy scale, EV. And then you can go little that side, ultraviolet, so it will be 5, 5.5 EV and so. So you see, the earlier I showed, the band gap was about 3.5 or so. So just with a visible light, you can excite one electron from valence band to conduction band. Nothing. You just shine a light and electrons will be, it will hop from valence band to conduction band. So now, if we shine, so before that it was some energy. Now we know this is light. So if you shine some light, one electron will be absorbed and it will be in the conduction band. As I told, one electron will be absorbed. So that's why it's called absorption. So you shine light, some energy, and the system absorbs that, and the electron goes from valence band to conduction band. Similarly, the process I described, it can come down and emit that energy. Ideally, you should say emission, but we face is like good names. We call it luminescence. It's just emission from the material. And then one thing can happen. You are not giving that much of energy. You are giving less. Then the electron has no place to go here. It's blank. So it will not absorb. So that light will transmit through the system. It will not be absorbed. And there will always be some reflection from the surface. There is no surface which is perfectly non-reflecting. So we artificially make surfaces which are not reflecting, but ideally, realistically, all the surfaces will have some percentage of reflectivity. Okay. So believe it or not, in our lab, these are so absorption and transmission are kind of complementary thing. So the thing get absorbed is not transmitted, the thing gets transmitted which is not absorbed. This is a complementary thing. So in our lab, we do some variation of these three things. That's all. Some light is getting transmitted, some light getting absorbed, some light it eats first, then emit, and some part is reflected. That's all. But in our lab, what we do is that we scan with light. So say this gap is 0.7, then we scan 0.7, 0.7, 0.71, 0.72 in energy. We can scan that. So this process where you study a property of anything over an energy range, this is called spectroscopy. It's just, again, a fancy name. The bottom line is that you are studying some property over an energy range. That's all. So we have people in our TIFR itself who uses a range of energies of electrons. So they call it electron spectroscopy. I use light. That's why I say it is optical spectroscopy. There are people who use fluorescence. They call fluorescence spectroscopy. But the spectroscopy means is that you study some property over an energy range. That's all. So this is a curve which shows. So this is absorption measurement. It's done in our lab actually. So this is absorption measurement on some material. I will come to that. But you see some peak here, distinct peak, and there is a small peak here. So it's basically the absorption measurement on some material. And these peaks are basically of that quasi-particle exciton. If the exciton was not there, then it would have been a continuous curve like this. But with the exciton, you have these distinct peaks. How it comes and all, just ignore that. Just you understand that because of that quasi-particle, you get this kind of peak. And the similar thing in the reflectivity, if you do the same measurement, if you see the energy range, it's kind of the same energy range. And this is reflectivity. So here I'm measuring, I'm shining light, how much is reflected back. So these features are because of same exciton. This is for another exciton. This is for another exciton. The same thing translates to reflectivity as well. Yeah. Yeah. No. Yeah, that is true if there is no object like exciton. So if you have a glass light and you shine light, then the transmission should be equal, the total light intensity should be transmission plus absorption plus reflectivity. That should add up to the transmission, the total energy of the light. But if you have a feature like this, a quasi-particle light exciton, they don't behave like a normal thing. I mean, they have some special property that we can discuss after the talk if you want. I can tell you, but I don't want to involve this in the general discussion. But it's not always true that, and also this is not absolute absorption. You see, we are describing it in some unit alpha D, but that is in percentage. Okay, so the units are also different. That's why it doesn't look like a complementary thing. Okay, any question till that? Any question on YouTube? Okay. Okay, then I will go ahead. Continuing with the same thing, optics is, as I told, like everything is how I'm doing on time. What is the time? 11:20. Oh, I have to shift gear. Okay, so we are dealing with light, okay, which is basically an electromagnetic wave. What does it mean? It's simple thing that light, whatever light we see, it has one electric field component and a magnetic field component, and they are perpendicular to each other. So if the electric field oscillates in this way, the magnetic field oscillates in this way, and when electric field and magnetic field oscillate in a perpendicular plane, that produce electromagnetic wave. Okay, so it's as simple as that. But because of this thing being an electromagnetic wave, it has very, a few peculiar properties. One of that is polarization, which will be very important in my talk. So that's why I want to explain this. So this red curve, we just follow this red curve, that is in one plane. So it is oscillating, but it is oscillating in this plane only. So that is the plane. But then this plane can be anything. It can be like this, and this oscillate on this side. And it can be anything. It oscillates here. Everything is allowed to be an electromagnetic wave. The only thing is the electric field should be in one plane. But that plane can be anything. But there is something which is called a polarizer, which restricts all other oscillations and only allow one direction of oscillation. So say all these things are coming, these things are there. This is called unpolarized. There is no specific direction to it. But if you put a polarizer with polarizer axis like this, then after that, only this polarization will go to you. All the others are either absorbed or something, reflected, something. But you will get only light, electromagnetic wave oscillating in this polarization. So I'm just showing you some image. So this is a linear polarization. Why it is called linear polarizer? Because if you see in this plane, it creates a line. That's why it's called linear polarization. But there can be other things which is called circular polarization, which is the electric field is actually rotating like a circle. That is called circular polarization. And there is something in between, it's called elliptical polarization. But the thing is, can we see polarized light? Can we see the polarization of light? Anyone have seen anywhere polarization of light? I think here. What? Where? Where you have seen? I can't hear you. Lab. Okay, no. I'm talking about everything. Some screens are polarized. So can you say whether this screen is polarized or not? Yeah. Exactly. So we as a human, we cannot detect the state of polarization of a light. We cannot detect. Our eye is not sensitive to that. To know whether this light is polarized or not, we need another polarizer to check whether this is polarized or not. So what will happen? If it is polarized, what will happen? If I put another polarizer. By the way, I have polarizer. I will test whether it is polarized or not. But what will happen if this is polarized light? So if it is linearly polarized, say, if it is linearly polarized, it should have some angle, because linear means it should be following one line. So it should have some angle. And if I put my polarizer along that angle, it will have maximum intensity. And if I go to the perpendicular to that, it will block completely. So in that way, you can check whether this is linearly polarized or not. To check circular polarization with one polarizer, it's not possible. But you can say one thing: if you take a linear polarizer and rotate on this, and if there is no intensity variation, then that might be a circular polarization. Might be unpolarized also, but might be a circular polarization. So let's check whether the screen we are seeing now is polarized or not. So this is a screen removed from the monitors. So all the LCD monitors are basically the final layer is actually a polarizer. If you can, so I think Ullas has done that. You have to with a very fine knife, you have to scrap this thing. So you can see, right? It increased or not? It's increased. So this is low, this is increased. Okay. So this screen is actually a polarized light. It's showing a polarized light. But our eye cannot detect. For our eye, it's normal. But it's actually polarized, and as you are getting minimum here, the polarization is in this direction. So it is a linear polarized light is coming out of this, which has a polarization axis in this direction. Okay. For an unpolarized light, I have two polarizers I'm giving to the audience. So for an unpolarized light, if you put the polarizer first, then this is a polarized light. And then if you put another polarizer in front, this you can block. You can test, just don't break this thing, return in the same condition. So that is basically the polarization of electromagnetic wave. So now we'll come to the next part, which is ultra thin. So at the start, at the beginning, I told like what is ultra thin. So what is the thin you can think of? So one is like human hair. Human hair is very thin. So this is a electron microscope image of human hair, and there's a mark here which says this is 10 micron. So it's roughly 10 to 15 times of this scale. So it is roughly 100 to 150 micron our hair. It varies from human to human, but an average that. If you divide this with how many zeros, and what is this? 10 lakhs. So if you take one hair and you cut it in 10 lakh pieces, one piece of that will have 1 angstrom. There's some different unit. That's all. So the material today we are going to discuss has a thickness of 7 angstrom. Okay. So if you consider as 10 angstrom, then it is 1 lakh times thinner than the thickness of your hair. And that is kind of ultra thin. What we mean by ultra thin semiconductor. So this is ultra thin. And actually, this is the thinnest semiconductor of the universe, not our world, not India, so the universe. This is the thinnest possible semiconductor. The name of the material is MOS2. So the kids here, they will know better. What is MO in the periodic table? Anyone? Molybdenum. You're not supposed to give answer. But then S, what is S? Periodic table, what is S? What is S? Anyone? Sulfur. So this is molybdenum, sulfur, 2 sulfurs. It's called MOS2, molybdenum disulfide. So it is a member of a class of materials called transition metal dichalcogenide, where basically MO is a transition metal, and there are 2 chalcogenides. So that's why it is dichalcogenide. It's just a name, a fancy name. So now we have understood the ultra thin and the semiconductors, the optics, and how I probe the ultra semiconductors using optics. So what is left is magnet. Okay. So now we'll describe about magnet. So immediately, what you can think of about magnet, where you have seen magnet? Fridge magnet. Fridge में लगाते हैं हम ऐसे. There are several things जाके लगा देते हैं. So what is the typical strength? So this is kind of a fridge magnet. So what is the, I have a fridge magnet here. So this kind of thing you have seen probably in the fridge magnet. So the magnetic field kind of it produced is 0.01 Tesla. Tesla is some unit, don't bother about that. 0.01 Tesla. There are materials, magnets available in the market, which is called neodymium magnet. This kind of thing, you probably have seen that. They have a little stronger magnetic field, maybe 5, 6, 10 times more than that. So it's order of 0.5 Tesla. But do you think that is the end of it? Can we make even stronger magnets? By the way, these are permanent magnets. Okay, so you cannot remove the magnetic property from them. Once it is magnetic, it's always magnet. But there is something which is called electromagnet. So you can produce magnetic field by by flowing current through a coil. So that is called electromagnet. So this is an electromagnet we have in the lab. So that can go up to 2.5 Tesla kind of magnetic field. So you see this is kitna 10 100 times more than a fridge magnet. Okay, but can we go even further? I have space left here, means we can go actually beyond this. So we have another magnet in our lab, which is called a superconducting electromagnet that can allow a huge current through it. So that can produce order of 10 Tesla. So in our lab, we can go 7, 8 maybe. But nowadays, people are producing 15, 14 Tesla magnet using superconducting magnetic field. But is that the limit? Can we go even further? Yes, we can. So then it will not be a fridge magnet or a bulky magnet like this, but the magnet itself will be a building. So just to give some comparison, so this is kind of my height. Okay, so the floor you can see. So this is about 5 feet kind of, and this is the magnet, this whole thing. And these lines are basically water lines. They push chilled water to cool the magnet, and it immediately gets hot, and then hot water is sent back to chiller again, and then chilled water comes, and there is always a cycle like this. And you need a building of chiller just to cool the water, and you need a building to put the magnet, and such a huge thing. So there are very few places on Earth. So if you see, it goes to 33 Tesla. And in this facility only, they have a magnet which goes till 35 or so. So this is there are very few places on Earth where you can go till this kind of magnetic field, 33, 35 Tesla. I was lucky to visit their lab. This is in Nijmegen, Netherlands. They have 6 such magnets. There they can regularly go till 33 Tesla. It's a huge magnetic field. But can we go further, or this is the limit? Now I have no space left in my slide, but I can always go to the next slide. And the thing is, we can go actually even beyond this. But the only thing, these all magnets I show in the last slide are steady magnets. So it's 2 Tesla, constant 2 Tesla for 6 hours, 10 hours you run, it will give you 2 Tesla constant magnetic field. But humans are creative, they can tweak things. So they have created a special kind of magnet, which is a pulsed magnet. So you put lots of energy in a very short time, and for that short time, you'll get a very high magnetic. So how short is like milliseconds. So 1,000 times smaller than 1 second. For that much time, you can create a huge magnetic. But that will be pulsed. You will not get it. And also, once the pulse is gone, you probably for 30 minutes you have to cool the magnet. And then once the magnet is cooled, you can again give one pulse like that. So the principle is simple. There is a charge bank. You put lots of charge. It's like charging our mobile like that. You can charge that, and the key is open, and there is only one loop of copper. And you suddenly switch this off, the whole current will pass through that copper, and that will create immense magnetic field, but for a very short time. But what will happen to the magnet? So there is a video. So magnet is somewhere here. You will understand where the magnet is. Let's watch this video. So the magnet was here. Now you understand. The magnet blocks. So you put so much of current through that copper blocks. And it actually happened, you see. This is the coil actually. And this is before experiment. Your sample is inside this. And after the experiment, it blocks. Your sample is protected. You can do another measurement. But for each measurement, you have to put one copper plate. And after one shot, the copper is gone. So this video, they claim that they produce 1,200 Tesla. But I'm not quite sure about their number. But what I am sure about is that this is a facility in France where they regularly can go to 100 Tesla, but for just 15 milliseconds. This is 15 milliseconds. For 15 milliseconds, they can produce a 100 Tesla magnetic field. This kind of the highest a human can achieve. Okay, so now we have understood all the individual letters, words. Now the time is for the combined words. So we have understood what is optics, and we have understood what is magnet. Now we'll consider magneto-optics. So what a magnetic field does to light? It can change the state of polarization of the light. How? Is that if you launch a linearly polarized light like this, and it passes through a medium which has a magnetic field, it can rotate the state of polarization to some angle. And similarly, this is in transmission mode. If you do the measurement in the reflective mode, you can launch a linearly polarized like this, and this surface is magnetized. The magnetic field direction is like this. After reflection, the state of polarization will be modified. So this effect is called Faraday effect, and that effect is called magneto-optical Carr effect. So my PhD topic is kind of this magneto-optical Carr effect on different materials. So till now, I'll stop for a moment because I'm thirsty. If you have any questions. So it proves either of one. One is that you understand everything. I am an excellent speaker. The other thing is you understand nothing. So that's why you cannot ask any question. I don't know what it is, whether I'm an excellent speaker that you understand everything, but I hope that. Okay. So now we increase our word length, and now we ask what a magneto-optics does on a semiconductor. So the fundamental question is, what is the effect of magnetic field on semiconductor, or largely on the solids? So as I showed you, there are energy levels like this. In semiconductor case, that is a band of energy. If you consider just two levels of such, and if you probe this system with two circularly polarized, so one is rotating like this, another is rotating like this. There are two circular polarizations. If you probe the system with those circular polarized light, you'll see no difference. Same energy. It will, if you do any measurement, they will give same result. But whenever this kind of thing happens in physics or science in general, we understand there is something underlying there which I cannot distinguish with two polarizations of light. So they must have substructure, which right now I cannot see. But how we'll open up those substructures? Their magnetic field acts as a kind of magnifying glass. So you apply magnetic field, and you will see the same levels are now splitted in two levels. So this splitting is called Zeeman splitting. Zeeman is the name of a scientist who actually first saw these things and described. So this is Zeeman splitting. Now, if you shine these two polarized lights, one is rotating like this, another like this. Now they will have distinct transitions. This red light only transfer particles from here to here. The green will transfer here to here, not here to that level. Okay. So by applying magnetic field, you lift the degeneracy which was there in this system. So in my case, my excitons in reflectivity looks like that. So for zero magnetic field, it doesn't matter whatever circular polarization you are using. But as soon as there is finite magnetic field, there will be a splitting because of this green polarized and red polarized light. And the energy difference between them, there will be some energy difference. And the only equation I have in my presentation is this, the 4-letter equation, 5 if you consider delta. Then this energy gap is equivalent to G, some parameter, mu B, which is a constant, and B is an applied magnetic field. So this G is a material property, and it is called Landé factor. Okay. So this amount of splitting, so what will be the difference between red and green, that is decided by obviously how much magnetic field you apply, but the material property which involved here is the G. The more the value of G for a given field, you will have more splitting. And yeah, sorry. reflectivity, sorry, I should have mentioned that. The reflectivity. So this is energy, this is reflectivity. Okay. So just take my words that more G is better. For a given field, if you have more G, this is better for us. I will explain why it is better at the very last slide. So, okay. So with that, I have just simulated a system. Nakli kuch. Okay, this is not actually happening. On mathematics, I'm just creating. So I have assumed energy difference, which will be milli electron volt. So the energy scale we are talking 1,000 times less than that, 5 milli electron volt. And for a G factor of 2.5. So this red and blue curve are for two circular polarized light, and I take a difference between red and blue. So if I subtract blue from red, I will have a peak. If I subtract red from blue, I will have a dip like this. But the thing is, I showed the 34 Tesla is available in some part of the world, but I cannot go there. What I have is a 2 Tesla magnet. So for the same system with a 2 Tesla magnet, what I will see. So if my magnetic field is 2, the G is same 2.5. Now the delta E will be even 1,000 times smaller than, it's not 1,000 times because 300. So 10 times smaller than, or it is 100 times smaller than the earlier value. And now if you see, you barely can distinguish between a red and a green, red and the blue. And if you subtract red from blue or blue from red, this is the graph. So here you see there is something, but it's buried in noise. You cannot say anything. So what can we do? I have only access to 2 Tesla. That's all. Either I have to go to France for that measurement, or if I do in my lab, then I should say I can't. But we are physicists, we are scientists. Whenever there is challenge, we try to solve that. So now the work I'm going to show you is actually my research work, what I've done in last 1 or 2 years is basically this. Is that you have a 2 Tesla magnet. You want to measure the difference between these two, basically this defect. How will measure? The energy difference is so small. So there comes the technique, which is a well-known technique, obviously. And now I will test one thing. So there are 2 boxes you see there. So one box is different from other in some aspect. Kuch to different. What is the difference? Try to imagine something. Yeah. Is there any difference between these 2 boxes? And I say there is a difference. Now you try to find out. Take some time. Try to imagine something, some shape, some very, okay. So now once you have a guide that is some shape, where is it? This one. This one is different. Okay. But to understand this is difficult. Okay. There is hazy something and there is, I mean, you think about it, when you are guided by something, you can say that there is a square. But now I'll show you a picture. Is there any doubt whether there is a square or not? Everyone can see the square. There's no problem. But here it took at least 30 seconds to detect that. But here is immediately, anyone will say there is a square. So this is the technique I have used. This is called a modulation spectroscopy, modulation technique in general. So is that, just to emphasize, so this noise level was 0 to 100. So there are color grids. So 100 is complete black and 0 is complete white. And in between, they have gray, different level of gray. So the value was 0 to 100. And this part is just a 3 added to that. So it's basically 3% signal over a C of 100. So here you definitely can see that. So it's basically a random C wave, which has a height of 100 floor, say, and you can see a signal which is flowing with that only, but it has an amplitude of 3 floors. So there's a 100-floor noise, but a 3-floor signal, that also you can detect using the modulation technique. So it is not merely subtraction of this to this. In that case, as I told earlier, you cannot get this 3% signal there. That will be completely, the noise will be even more than this noise. It's not a mere subtraction. It directly measures the difference, not one curve minus another. It directly measures the difference between these two curves. Why you can detect this? Because this background is constant. Here, your brain is seeing this and then this. But here, those are superimposed. They're on the same scale. The background is not changing. Only the difference you see. So noise is same there. Same noise, but here your brain can see the difference between these two. So it's not subtraction of this from this. This is superimposed. And it's a GIF. It is continuously changing those. So in our measurement, we are not measuring, we are not subtracting with field minus without field. We are measuring the difference because of the magnitude. That's why our sensitivity goes, immensely high. We can detect very, very minute signal over a very large background. So the modulation spectroscopy, the technique is that the parameter we want to measure, we perturb the parameter with a known frequency to me. So I know that I'm perturbing that system, disturbing that system in a say 60 hertz or 10 hertz. So I know that whatever disturbance I'm creating, my signal will come and that frequency only. Okay, I'm disturbing my system with light, say at 100 hertz, and I know my signal will come in 100 hertz only, not in any other frequency. And that's why we increase our signal to noise ratio extremely high. Okay, so what is the time? 10 minutes. Okay. So, so what we want to measure? We want to measure a very small energy change. I showed you in that scale. I want to measure 300 micro electron volt, some energy, but I want to measure 300 of that. And that is because when there is no magnetic field, there is no gap. With a magnetic field, there is gap. So I want to measure the gap, the energy difference. So I will modulate my magnetic field itself. There is not a steady magnetic field, but an oscillating magnetic field. But oscillating a 2 Tesla magnetic field is impossible because 2 Tesla is a huge magnetic field and you cannot oscillate in, say, even 10 hertz, which is a very low frequency. So in 1 second, 10 up and down, it cannot do. So that's why we have built this small coil in our lab, which is, this is this much. So in image, probably you cannot see, you cannot estimate. So the magnet is like this small. And we have some specific circuit we have made in our lab only. With that, we have a magnetic field of 50 millitesla. So it is order of this neodymium magnets. Okay, so those shiny ones, they have a constant DC field of about 50 millitesla. So this produces the similar magnetic field, but it is oscillating. This is not a constant magnetic field. So this is just a circuit to impress you that I have done something. But an expert will say that it is very simple. There is no complicated part. All the parts are available in all optical spectroscopy labs. It's a very simple thing. And we have made this setup. And for non-science audience, it might be very attractive. That's why I have put. There is no physics associated with that. So now this is the reflectivity curve I showed you before. So now the question of what is the question I'm asking? What is a thing I'm curious about? So these two large features, these are corresponding to 2 excitons that people know from, for decades, even more than decades. When the people have started to work on this material, they know these two are 2 specific excitons. But okay, there are 2 types of excitons. But the Question is, what is this small feature, A star, what we are calling? So that is the question we are asking. So these two we know, but what is about this? It's not like we are the first person who are trying to answer this question. There are several groups. In past, there are reports in 1978, 80, that kind of time. People have measured this and they have said something. And in 2010, about when again people regain the interest in this material, they studied this also, and then they discarded the previous logic, previous explanation, and they gave some explanation. What is that? But all of those explanations they have proved wrong with time, with a better measurement. Okay. So we applied this magneto-modulated reflection spectroscopy, whatever we call this. So we have applied this technique on this material and try to answer whether can we contribute something to this debate. Well, like, what is this? What is coming from? So we have done this MMR spectroscopy around this part only, so covering only A and A star. And just forget about blue, just concentrate on red. So for this A feature, you have a peak like this. For this small feature, you have a dip like this. So just by looking at it, you can say, like, whatever is happening in this A, that is happening opposite in A star. It is giving rise to a peak for A, but for the same condition, it's giving rise to a dip like this in my spectrum. If you, again, now forget the red curve, concentrate on blue. For A, it is going down, but for A star, it's going up. So whatever is happening, or the opposite thing is happening for A and the A star. And from this, somehow, if any of you are interested, I can describe you how we extract this. But in a public talk, I don't want to involve mathematics and all. So you can actually extract the Landry factor, what I told you before, from this curve actually. So we have estimated the Landry factor for these red dots are for this peak, and the green dots are for A star. So now you see the value for red, it is minus 2.5, and for green, it is plus 9.7. So now you understand one is negative, another is positive. So that's why for one, it is peak, for another, it is dip. And also the value is very high. So 2.5 is, if you consider 2.5 is small number, then 9 is 4 times of that. But the most interesting about this curve is that you see the y-axis. So in this y-axis, I have measured some energy difference, which are, say, 6, 7 micro electron volt. If you see in the green, I have measured 20 to 30 micro electron volt. The technique I described earlier, we could not see anything for even a 300 micro electron volt, 10 times of that. Even with the previous technique, you cannot measure a 300 micro electron volt difference. But now with my technique, I can measure a 10 times smaller splitting with this measurement. And you see the signal to noise ratio is very good. It's not like it is buried in some jungle and I'm saying that there is something. You can definitely say there is a peak and there is a dip. So my technique is better. So I think this is what I've described. So what is the physics underlying between this positive and negative G factors? There is some theory which says that in this material, if this is a layered material, so this is the monolayer I told, this is 7 Armstrong thick, but then it can stack on each other and it makes a bulk. So one exciton can be like this, that electron is in one layer and the hole it also is in that layer only. So they are bound in this layer. This is called intra-layer exciton. But the theory suggests, so for this kind of species, the G factor is supposed to be negative. But if we consider the electron is in one layer and the hole is in the other layer, this is a possible case. So in that case, they will form an exciton, and this is called interlayer exciton. But this interlayer species, the theory says the value should be positive and large. So once we got this result, we are sure that this A star feature, which was debated, like what is the origin of that? Now we can assign that to interlayer exciton. Who knows? Maybe 10 years down the line, this will be proved wrong. But till now, what we understand that A star feature is because of this interlayer exciton. So what, like whenever we get something new result in our lab, what we do, we have done that. We have published in a journal. It got accepted last year around June. Oh, it's written there. Actually, it's published on 22nd June last year. Okay, so I've done a great job. I have measured a very small energy difference, which people cannot measure. Now, the biggest question by knowing all this is, so what? What have you done? You have measured something very low energy. That's all. Okay, fine. So, to give the background of why we are working on this material, there is something, a law called Moore's law, which is not actually a law, but Gordon's Moore. So the Moore is someone's surname. So Gordon's Moore was probably Google's something. I don't remember. But in some conference with semiconductor industry, he showed a curve that history says that in each decade, in each 2 years, the number of circuits in a specific length, it doubles. So, which means that the chip you have now, if it has a 10,000 transistor in it, in 2 years down the line, that same transistor should have 20,000 chips. That is the kind of guideline to the industry that, same chip, 20,000 transistors in this. Thanks for that. So the same dimension, physical dimension is same, but my calculating power is twice. So it should follow that line. And astonishingly, though it doesn't have any science behind that, but always industry tried to follow that. So in 2 years, you have to double the number of chips in a physical dimension. Until now, we are actually following that. So every 2 years, the number of chips is actually increasing and at the same rate. But there is a hint that in next few years, we probably will saturate, will not be a straight line, but a little bend with that. So in the same physical dimension, you will not have twice ICs. So what is the problem? There are multiple problems happening because the circuits are so small. Now one circuit is talking to another circuit, and I mean, there is no technique you can write physical circuits on such a low dimension. We have gone to that level. We cannot go beyond that. So it is extremely low physical dimension. And also there are excessive heating. So you know these servers all over, like we also have servers in TIFR. Like they have a building of AC just to cool that room because the server is so heated up. As soon as the one AC is switched off, aag lag jayega. It's so hot. So there are other problems also. There comes the importance of this material, that it may happen. There's this class of material TMDCs, the material I work with, MOS2. They may help us to overcome this challenge. How they will overcome? They are much efficient than silicon. The silicon is the material we use. In some niche area, gallium nitride kind of semiconductor, gallium arsenide, other kind of semiconductor, they are used. But mostly it is silicon. And in some aspect, it's written there if you're interested. But in some aspect, my material is better than silicon. It has extremely rich spin properties. So I have not gone to that. Basically, electrons may have charge as well as a spin. So it has extremely spin properties, which make it a promising material for a completely, paradigm shift, which is called spintronics. So now we call it electronics, but there is the concept of spintronics. So these materials are very promising candidates for spintronics. So our finding, this large G factor of interlayer exciton may come to helpful if in future people try to make devices for spintronics. So now it's a kind of research is going on, like without considering one electron flowing, can we consider exciton as a species and carry the information? So what will be happening, because exciton is a charge neutral particle, because it has electron and hole. So as a whole, it is a charge neutral. And if you know the heating is proportional to the current is because of charge. If the particle carrying information is a chargeless particle, there is no heating. So that is the kind of principle. So in that case, the excitonic devices, interlayer exciton is an extremely suitable species to part up with, to give information in interlayer exciton. And I'm not throwing words. This is a paper from 2022. If you know this company, this is the company which has almost 90% cap of the total world production of microchips. And they and Intel are kind of the two giants who can produce this kind of fabrication. They have fabrication facilities. They have published something in 2022, and they are actually working on this MOS2, monolayer MOS2 materials. And who knows, 10 years down the line, you may have your mobile phone running on the device I am working with. Who knows? So obviously, if the question is so what, the answer I will give is that we don't know yet, obviously, but it may happen. And I request you to go through this beautiful quote by Carl Sagan, where he says that it's obviously the society will choose which technology to pursue. There are obviously several things like MOS2 and thousands of other semiconductors. Which technology to pursue, society will decide, obviously. But if we don't do fundamental research just to, to feed our curiosity, I just want to do this measurement because I want to know. That's all. If we don't do that kind of research, then society will not have an option to choose. So if we have thousands of options, society can choose one. But society to choose one, you should have thousands of options. So we as a fundamental scientist, we are creating those thousands of options. And who knows which technology will be picked up by society, the companies, we don't know. But for that reason, to create thousands of options, we should continue to do the kind of research we are doing. So Professor Sandeep Ghosh is my guide, under which I am pursuing my PhD. And I was privileged to have two extremely good seniors of mine. So Vishwas was a PhD student in my lab, and Dibyasankar was a postdoc. I have spent, in my budding days, I have learned all the technical things from them. So I'm thankful to them. And this is our lab website. If you want to visit what we do, you can visit there. And these are the places where you can find me. Drop me a mail or send me a message in any of these platforms. I will try to answer those things. And thank you for your attention for this question. But the thing is, it has a lag between here and YouTube. So the person will not able to see. I mean, we'll see later. Is this that slide? What is the question? Oh, okay. Yeah, this is, if it was a conference talk, I would have been very careful and look this thing. Ideally, there should be a factor here, which is called the magnetic quantum number. So it should be MJ G mu B B, and that MJ factor is different for different materials. So it might be half in some material, it's half, in some case 3/2, 2, this kind of things will be there. But I mean, that's a constant. So I should have written this as a proportionality constant, otherwise. So,
So nice catching. And second question is about graphene. Okay.
yeah. So okay. So I'll repeat the question. So graphene, whether can it be
Can it actually be a competitor to
MOS2?
along with this, can it offer the alternative?
Yeah. Yeah. So the thing is, I work with MOS2. The person who works, so we have lab who work with graphene. If you ask them, they will say, yes, that is the future. And I work with MOS2 and I would say, no, this is the future. And but there is a catch while I'm saying this is the future, is because this is a semiconductor material. So we know various things about semiconductors already, but graphene is the only drawback of graphene is that it doesn't have a band gap. So it's not completely metal also. It's a kind of semi-metal, it is called. It's not completely metal, and then it's not a completely semiconductor also. So in that case, MOS2 is little better because it is already a semiconductor. Graphene cannot beat in that case, but there are ways you can make graphene to semiconductors. Okay, by applying something, you can make graphene, and there are companies, startup kind of, they are now actually working on that aspect also. Just by putting electric field, magnetic field, can we make graphene a semiconductor device, a semiconductor material, and do all our
So that's why you're thinking about having alternate technology.
exactly. Yeah, that is one of those 1,000 alternatives, and we don't know what will be chosen. Yeah. And about this flexible electronics part also, graphene is obviously can be used as a flexible material, but this material can also, because the thickness is order of that. So if you think about flexible electronics using graphene, then the same device can be made with MOS2 also. The added advantage is that it's the semiconductor. Okay. Let's stop it.
So thanks, Vidya. So nice talk indeed. So 2 weeks from now, there will be a talk. We are closing the online session. We will take online audience. Sorry, people will go child for you, but people here will get a chat. Thank you very much.
Okay, I had this. I forgot to hand it over. So there are two